All right. Hi, everyone, and welcome to the MQC Frontiers in Quantum Information and Technology seminar. This is the first seminar of the spring 2024 semester. We're excited to continue. Joint seminar with Michigan State University, University of Michigan, and Purdue. Today, we're very excited to have Alen Senanian from Cornell tell us about the recent experimental work using microwave signal processing to do some machine learning tasks on an analog quantum reservoir computer. So, Alen, if you're ready, the floor is yours.
Okay, great. Yeah, thank you for the introduction and thanks for the invite. Yeah, so I'll be talking about some work we put out on the archive over the break, over winter break. It's a couple of days after Christmas, which was fun. Yeah, so as Ryan mentioned, this is a work where we basically do some experimental small-scale demonstration of machine learning um, with superconducting qubits. I'll start with summarizing sort of like a very high level picture of machine learning. I'm sure many people have seen a lot of this stuff, but maybe I'll just focus it towards ideas that I'll be talking about later. Um, so yeah, modern machine learning involves these deep neural networks, where deep just refers to layers, many layers of neural networks, um, where these neural networks perform these hierarchical computations from some input data. So here's a schematic representation. This is, I believe, Logan's dog, picture of Logan's dog. Um, and yeah, so you have some input image that you feed in into these layers, and the output of the neural network tells you, for example, whether the picture that was fed in is a dog or a cat. Um, and these neural networks are typically the layers in these neural networks typically consist of some linear matrix multiplication um, combined with a nonlinear activation. So you have some nonlinear function acting on each of these nodes, and then the nodes are connected with some weights, as they're called, represented by a matrix. Cascading these layers basically just allows you to create a nonlinear complicated function that's highly parameterized that you can then train to perform the computation. And of course, the, um, the construction is so that you can also perform these gradients in order to do your updates very, very efficiently. Um, so yeah, each of these layers is just some nonlinear function acted on uh, some parameterized matrix on the input from the previous layer. The point I want to make though is that this neural network is basically just some very parameterized nonlinear function, and that some generic analog system, especially particularly nonlinear analog physical system, can basically be used to mimic this behavior. So you have some input, you have some parameters that you may choose to train, and you have some output. And this is sort of the subject of some work from our group that shows how to train various physical systems to do machine learning tasks. So for example, so your input could be, imagine a billiard ball table. You have inputs encoded as positions of a set of billiard balls, and then some intermediate balls are the parameters of the system. And then the positions of the final billiard balls tell you some information about the output, which includes like the computation you want to do. And this is just one such example. But you can think of, tons of different examples. So again, this work, they sort of demonstrated three different physical systems and showed that you can actually just train these different physical systems um, with some methods that were introduced to that paper. But the sort of the high level picture is just the idea of a very analog uh, approach to parameterizing and performing computations with physical systems. Um, so, for example, another example, um, here we have like some 2D data set. These orange dots belong to some class, and then you have the purple dots belonging to some other class. And it's some two-dimensional space that you encode in 2 degrees of freedom in your physical system. And you have parameters. This is basically a set of coupled pendulum. And here, the orange ones are extra pendulum that sort of encode the parameters that you would train or not train. And then so the input is encoded in the relative positions of the red pendulum and the blue pendulum is your output. And so here is sort of a heat map of, suppose this is the training data, this would be, the sort of the space of showing like where the decision boundaries of this trained system would be. The other point, well, there's sort of a number of reasons why you would want to do this. Particularly, let's say, our group focuses a lot on making neural networks, physical neural networks, have optics where you can save a ton of energy. I don't think we can sort of make the same claim yet for superconducting qubits living inside a Zoe bridge. But the other reason why you might want to do build machine learning systems out of physical systems is you can directly interface with inputs that are of the physical world, not digital inputs, but you can sort of perform classification directly on physical and analog inputs. So okay, so how would we like to generalize this performance system? So of course, there's the whole field dedicated to figuring out how to do machine learning with quantum systems. Some of it is sort of based in the sort of fault tolerant regime, where we'll be maybe we'll be some number of years from now. And then there's another set of work that's focused on coming up with practical applications in the near term using sort of noisy quantum systems, mixed devices that they're called. One such sort of proposal is known as variational quantum algorithms. This is not the only sort of, by any means, the only sort of quantum machine learning application, but this is sort of a very popular one. And I'm sure many of the audience knows about this, but the variational quantum algorithms or variational quantum eigensolver involves sort of preparing some quantum state, and then you have some Ansatz layer that is parameterized by parameters that you're going to train, and then you have some sort of measurements which you feed into a classical computer. And this layer you can sort of think about as a neural network, and there's demonstrations in optics and ion traps and so on. It seems like people should feel free to correct me if I'm wrong, but it seems like the field is sort of converging on that VQAs might be sort of challenging to implement with noisy or NIST devices, particularly due to barren plateaus, especially as the system size increases. And and hardware imperfections or noise, which can change the sort of cost landscape, or even change um, where the minimas are. And so this has sort of been challenging to sort of demonstrate an experiment at sort of a highly practical level. Um, so um, so this brings me to basically the outline of my talk, which is about using a framework known as reservoir computing for quantum machine learning, which I'll describe. Um, After a quick introduction of reservoir computing for quantum systems, I'll talk about how we implemented it, and I'll go through an example classification, basically a binary classification task. And finally, I'll take a look at, or I'll go through some what are supposed to be closer to real world or practical applications um, um, of classification on microwave signals that are directly interfacing with our systems. And then I'll talk about sort of the outlook. Okay, so yeah, I'll start with just summarizing reservoir computing. Um, so yeah, so we have some for the types of problems that we're studying here. We have some input data, some classical input data, and this is going to be a sort of time series, some sort of time series. This makes it sort of natural for reservoir computers. I'll explain that in a moment, but so we have some classical input data, which we continuously inject into our physical reservoir, which we can instantiate as a dynamical system. Reservoir computers were initially inspired by recurrent neural networks. So I think the history was initially explored in the digital domain, but for reasons that will be clear in a moment, actually implementing this with a physical system has some nice things about it. And then as this input is continuously fed into the reservoir, and the reservoir is performing some nonlinear dynamics, you perform measurements, and from these measurements, you train a linear estimator. This is basically just a single matrix, and this is the only part of a reservoir that's trained. Okay, so it's a matrix of like the features. And the really nice thing about reservoirs is that given that this is the only thing that's trained and there's no nonlinearity after this, the training is it's just basically a matrix inversion. It's super fast and yeah, very easy. Yeah, so yeah, as I already mentioned, the reservoir itself is totally untrained, and it's the only purpose is to take this perhaps low-dimensional input into a very high-dimensional space with some nonlinear dynamics, which the linear estimator can then just easily separate. You can think of just exploding like the initial set of points, and then being able to slice through in a very high dimension. So I'll just go through a super simple example, which I'll have experimental results later for when we actually did the same task. But here we have some two-dimensional input. We have a distribution of one spiral arm colored in pink and another spiral arm colored in blue. And these are just a set of two-dimensional points. And then, yeah, we send in one of these points into our dynamical system, our physical reservoir. We send that to the linear layer, and then we'll get some outputs. And so this linear layer is trained so that you can sort of maximize the amount of times you can think, right, more or less. So for example, here, this would say that this input indeed belonged to the spiral arm. This has the sort of higher weight. Okay, that's sort of the high level idea for a physical reservoir computer. Now, what if we make this quantum? And this was pioneered by Kojima, Fuji. Um, and there's sort of a couple subtle things we have to keep in mind. Number one is that for a quantum system, like each of these measurements are, stochastic. And so we're going to have to sample many, many times in order to reduce expectation value. But the really nice thing about this scheme is that, since all the training is done on sort of like a digital, something on your computer, basically, this digital in your estimator lives on the computer, you're sort of much less sensitive to band plateaus and hardware imperfections, or sort of, you can think of as part of the dynamics. Right? They're not sort of used in any sort of gradient calculation. Right, this is just trained with a matrix inversion. For classification, train with a matrix inversion, or you can actually do backprop, but it's sort of a detail. For most cases, a simple matrix inversion is enough. So yeah, that's sort of the high level idea and motivation for why we implemented a quantum reservoir computer. I'll just go through and explain the experimental setup and the control drive stuff. So our physical reservoir is quite a simple system. It's not the Falcon chip from IBM. It consists of a single transmon qubit coupled to a oscillator. There's another oscillator here, which we call the readout resonator. This you can sort of ignore. This is only used for performing measurements of the qubit. Later, I'll talk about exactly how this works. We just go through that. But you can, for most of the talk, you can sort of ignore this readout resonator, and we just have like a qubit coupled to an oscillator, so sort of like the traditional James Cumming Hamiltonian, basically. The interaction is this cross-Kerr interaction or dispersive interaction. Basically, the frequency of the qubit will change as the number of photons in the oscillator is more and more populated. It's actually the same exact interaction that we use to probe the state of the qubit, because in reverse, but if the qubit is spin up, then the frequency of the oscillator, the readout rate. So yeah, so we have the qubit as the sort of nonlinearity of this subsystem here on the left. And why are we using cavities instead of just having a bunch of qubits? Well, yeah, I guess partially because we're not IBM. Oscillators are sort of a very hardware efficient way of getting large Hilbert spaces without having a chip 10 to 20 of qubits. Here's a picture of the device. This is the 3D cavity. It's made up of very high purity block of aluminum. It's quite literally a piece of metal. Nothing special about it. And then the inside sits the transmon chip. And there's a big hole here that stores the electromagnetic mode of the oscillator. Yeah, so just a little more detail into the experimental setup. For the results presented in the paper, we generated our microwave signals with a DAC, a digital to analog converter. But that's sort of like in principle, which I'll get to sort of at the end of the talk. This can really be a wide variety of different things. But yeah, so we have some arbitrary waveform generator. which we upconvert to be nearly on resonance with the storage, this oscillator, the cavity oscillator, using an IQ mixer. And then we have additional control lines that importantly we don't train, right? This is a reservoir computer. But these sort of enrich the dynamics of our system in particular ways that we sort of using sort of physically motivated design principle. It's the way to describe it. But yeah, so these are additional controls, additional pulses. But this section here is the input, the thing we're trying to classify. The readout of the qubit is, as I mentioned previously, you probe basically the frequency of the readout resonator. That goes down the bridge and comes back up, and you basically get a histogram you get samples, but you can generate many such samples to get a histogram and threshold the analog sort of signal you get to get a 0 or a 1 corresponding to the qubit. Okay, so that's sort of very generic to the entire field. It's sort of very standard way of reading out the qubits. But yeah, so there is some like nonlinearities happening here, but importantly, nothing is being trained, right? The only thing being trained is, I'll reiterate later, is a linear layer at the end of all of it. Here's a sort of schematic picture of that 3D block of aluminum. Inside is this hole and this stub sticking out. This is known as a stub cavity, a stub 3D resonator. And yeah, there's this pocket where the transmon lives, and here's a drive line where we can input the data. So yeah, we send the inputs to the cavity. This is probing the cavity directly. You can think of these as, you can basically think of it as some time-dependent displacement, which we, just like previously, this is continuously being done. And we, while this input is fed in, we're performing measurements, and this sort of scheme is repeated. Yeah, so we perform this block here of these measurements m times. Importantly, repeating these measurements will lead to different results as the input continues to stream in. You're no longer have the same quantum state as you sort of evolve through this circuit. But yeah, so each sample, each snapshot is some bit string. And then we repeat this entire thing with basically a reset in between n times in order to get these expectation values, right? So then you can ask, what are the, like, okay, we can take the results of these measurements, and we can just average over them directly in order to produce our feature that we send into the linear layer. But it turns out that that's not very ideal, especially without any sort of feedback. So instead, we actually, from these measurements, these raw snapshots, we generate output features from correlations. So this is sort of a schematic picture of our output feature, where we construct the output feature by calculating central moments of the statistic, basically. So we compute these central moments. So for example, this mu1 is the average over these m measurements, which are then averaged over m times, right? This is the covariance. So that's a 2D matrix. Here is like, this element here is the first measurement multiplied by the second measurement, and then averaged over repetitions, and so on. And then it's the third order central moment, and so on. And we kind of just concatenate these. There's degree of degeneracy here. These are all symmetric matrices, so we just grab the anti-symmetric parts, whatever. But we construct these output features from concatenating these central moments. And sort of the point of that is, well, you don't need, you're sort of able to capture the correlations, at least in sort of a successive way, right? Like intuitively, you expect sort of the lower order moments to have like noise, so you can successively grab more and more or higher order correlators to construct your alpha features that capture eventually the essential correlations of the system as it evolves, right? Okay, I hope that's right. So grab some water. Um, in a in the sort of literature of reservoir computing, I think having extra drives is maybe not the most common thing. You just sort of have your input, you have some dynamical system that then does some complicated stuff, and then you measure it. For us, that sort of wasn't enough. We needed to, spice things up a little bit by adding entangling gates, and so on. So now I'll just go through basically the combined unitary that we implement. So yeah, so we have some. So we start out our system in the vacuum. This is a schematic of the state of the oscillator, like a Wigner tomography. Here it's at the origin. We do a conditional displacement where basically the oscillator is displaced conditioning on the state of the qubit. And then from this point here, we send in our input. So if it was in G, this will send it over here, and we do a pi pulse, and then the excited branch will be sent over here. I guess one thing that's maybe not so immediately obvious is, this oscillator has some particular frequency, and when you send in a signal at some frequency, that frequency is conditioned on ground or excite, whatever. So the reason why the input is also conditional, that's just like the natural interface for how you would drive the system. But okay, so that aside, we send these the input is sent. Sorry, the input displaces the one branch, and we do a pi pulse on the qubit, and then it displaces the other branch. And then we undo this conditional displacement and come back here, and we let these different paths interfere, and this encloses an area here. The reason why we do this sort of complicated procedure here is basically when we were trying to come up with these different drives, one thing we found was that like most traditional measurements people do of a qubit oscillator system is sort of insensitive to the phase of the oscillator state. However, this entire procedure implements this geometric phase gate where the area that's enclosed by the oscillator state throughout this evolution is proportional to the phase of that initial input. And this area is then mapped onto the qubit, which we can then just measure very easily. Now, all of this stuff is like particularly these two components. This is for time-independent signals, which we do time-independent signals, but we also do time-dependent signals. But I just want to mention that this argument doesn't hold quite as strongly for time-dependent signals. That's sort of the detail. After that qubit measurement, which tells us some phase information, we have a parity measurement. And a parity measurement basically projects the oscillator onto either even or odd clock state of that oscillator. And so this parity measurement kind of lets you pick up changes in the photon number, and so it's sort of like an amplitude sensitive measurement. Here's sort of phase sensitive measurement. And additionally, the parity measurement also imparts a pretty non-Gaussian operation on the state of the cavity, right? You're collapsing onto even or odd clock states, and I'll have plots of experimentally measured Wigner functions of the state of the cavity throughout this machine. Okay, cool. So that's sort of the everything you need to know for in order to understand the result, hopefully. So I'll go through and sort of explain the reservoir for an example binary task. So again, we have this spiral classification task that I showed earlier. You have, again, two-dimensional points on some 2D plane, and they're arranged in sort of spiral arms, and we're going to send information like this information into our system, and we're going to try and classify whether that 2D point was from the pink arm or the blue arm. Okay, so how do we encode this information? Well, these are, as I mentioned, the input data is a displacement. So concretely, for those of you who are not aware of what I and Q means, it's sort of a terminology from communication engineering. But it basically stands for in phase and quadrature phase. So you can think of just two orthogonal carriers that contain some information. But each point you can just think of as being in the complex plane. And so this point, for example, has no I component, has no in-phase component, it's fully in Q. And so here's an example of what that looks like. This is the opposite. This is fully in I, there is no Q. So yeah, so these are basically a set of signals that we send in and drive our cavity here. An important part of this task is that a linear layer on its own, like if you took, a set of these 2D points and just fed it into a linear layer, which would be a 2x2 matrix, cannot do better than 67%. It does slightly better than random guessing, 50%. But if you orient this line, which sort of tells you the plane of separation between the two classes, you can kind of imagine there's no way to have all the blue points on one side, all the pink points on the other side. Putting it right here on the x-axis, though, lets you get away with 67%. I think full vertical would be 50. But yeah, so like I mentioned, this is we send these into our system, particularly the cavity, and we call this a time-independent task. I did have a frequency here and some time signal here, but we're driving it on resonance when you sort of are in the frame of the cavity. That basically looks like a time independent signal, okay, when it's on resonance. So these are fed into our system, and then we perform these measurements, as I mentioned before. Here is sort of like what the state of the cavity looks like throughout the evolution. And you see, for those of you familiar with Wigner functions, I should have explained this a little bit, but this is sort of the vacuum state, oscillators at the origin. Here you're getting some blue regions, which indicate Wigner negativity, which is purely quantum phenomena. And this is primarily driven by the back action of the parity measurement, and so on. And then you keep going, right? It gets more and more complicated. So that was just the window into the dynamics. But yeah, we repeat these measurements and we construct our feature vectors. And we send that into our linear layer, which we train with backprop or pseudo-inverse. And we get this accuracy curve as a function of the number of shots. And so you see that as you increase the number of shots, you're better able to classify the task, less subject to noise, right? Sampling noise. And there's a few different so this sort of construction of the feature vector, there's many different ways of constructing it. This will sort of different ways will lead to different scaling of the accuracy with the number of shots, and we found that doing things successfully in terms of the central moments actually have this really nice property of being able to get higher accuracy at lower shots. Here's a little fun experiment we did regarding this task. Remember that readout resonator we had? Instead of only using it for readout, we can actually use it to probe the quantumness of our system. So here in this experiment, we sort of populate the readout resonator, which is coupled to the qubit, with photons. And this readout resonator is very, very strongly coupled to the environment. That's how you do sort of very quick measurements. And as you populate this readout resonator, you're dephasing the qubit, right? Because the frequency of the qubit depends on the energy of the qubit depends on how many photons are in here through that cross-pair interaction with this dispersive interaction. As you populate this readout resonator and you trace over it, you're dephasing your qubit. You don't even need to I think trace over it because it's so strongly coupled to the environment. The photons in here are depopulating, populating pretty rapidly. Anyway, so yeah, so we pumped this readout resonator, and we observed that indeed the T2 of the qubit decays as we put more and more photons in here. And then we redid this experiment here as a function of this qubit T2 that we control experimentally. One thing we noticed is that, yes, indeed, as the qubit T2 goes to 0, the memory and the system sort of fades away, and you're not able to do well. You're not able to do well at all. But an interesting sort of consequence of our scheme, namely that we perform these multiple measurements during the evolution, is that the T2 only started to sort of impact things once it was on the order of the time between these objective measurements of the qubit. Okay, so this is sort of the example classification. Now I'm going to go into something a little more non-trivial, which is classifying radio frequency digital modulation schemes. So these are basically these are how communications protocols encode digital information. For example, super simple example, it's binary phase shifting. By the way, when should I be stopping? 50 minutes?
We have a full hour, so we have about 20 minutes left.
Okay, great. Yeah, so just an example here is like encoding binary numbers as basically the two phases of the signals. These are the I and Q quadratures again. Here's a much more complicated encoding, 16 amplitude phase shift keying. I I didn't know about this stuff until we were looking at sort of potential microwave applications. But yeah, there's a whole industry dedicated to it. Uh, anyway, this is what the signal looks like in the time domain. And yeah, we will send this to our 3D cavity and try to classify it. So one sort of difference with this task compared to the previous is now this signal is changing throughout the reservoir. And we have these multiple measurements where previously we have the state changing. That's of course still true now. But another thing is that between repetitions, so between where we reset the system in order to generate our statistics, we don't send in the same input. We just let this long time input stream into the signal or into the system. And so every single repetition is sort of slightly different. You not only have sampling noise, but you have basically data signals. For this particular task, we basically just had random binary bits generating the signal. And like all other tasks, the signal was on resonance with our cavity, our oscillator. And we set a symbol rate of about 1 megahertz. Sorry, the symbol is, so like the symbol here corresponds to like one of these changes or like sort of time bins that encode some binary number. And yeah, we set this to be about 1 megahertz, which is roughly on the order of the interaction strength. And oh yeah, and as I mentioned, we're not just repeating the signal, which could feel maybe a little artificial in sort of a practical application. Although this is not super practical either way, but yeah, we wanted to sort of keep the input streaming in and try to do classification without having perfect resilience. Here are some more, here are some examples of the different classes. In total, we have 10 different classes, and these are different time traces of those classes. So you can see it goes from the pretty simple to pretty complicated. And yeah, these are sort of broken up and sent into our system as a function. So here's the results for this 10 class classification. In about a millisecond of the received signal, we get about 90% accuracy. This is the accuracy of the function of shots. Sorry, this is the gray dashed line here is the performance you would get with just a linear layer. So imagine skipping the reservoir, you just send in the data directly into the linear layer, which is now much bigger than it was with the spiral case, but still, you will do very poorly. And here is a confusion matrix, which is a common thing people plot in ML. Basically tells you how well the system is able to distinguish between particular classes in the data set. And you can see at it's like 30 shots, it does pretty poorly. And as you take more and more shots, it starts getting the sort of simpler looking signals, right? But it still confuses the very complicated ones. But at sort of a very high number of shots, we can easily classify amongst the 10 classes. Cool. So one more task I'm just going to walk through is this is sort of meant to be like if the spiral class was, that was totally time independent, this phase shift, this digital modulation was sort of quasi time dependent, you have these discrete time bins. Now we're sort of going full analog. So here we have essentially white noise. that we pass through uh, uh, a time window filter, um, moving average filter. Um, and we have three different types of filters: a Gaussian filter, we have a Gaussian window, then you sweep over this license signal, a Lorentzian, and this 1 over 1 plus x, which we call inverse uh, uh, filter. And we do this for different widths of the filters, okay? So here's an example um, of the Gaussian noise or the Gaussian filtered noise class. Here is a 50 nanosecond filter width and a 600 nanosecond, much longer time scale here. And so from this, we have three sets of filters and two sets of filter widths that generates six classes. Um, so our reservoir is going to try and distinguish between the six different classes among these very, very analog looking signals. Right. So again, yeah, these are broken up and sent into our system as measurements are interspersed throughout. And yeah, I guess importantly, maybe importantly, yeah, I guess it connects to something. The 600 nanoseconds is sort of chosen to be on the order of the measurement rate. It's about half the measurement rate, more or less. But as I'll get into a moment, it sort of tells you about like if it's able to distinguish between different 600 nanosecond signals, there's sort of the correlations between the measurements to sort of help you out. I'll get into that a bit more in a second. Cool. So on the right here, we have a singular value decomposition of the output feature space of the six different classes. And we see the blobs sort of very well separated. Initially, remember, these are all noise. So if you were to do the same plot for the input side, these would just be blobs stacked right on top of each other, maybe with different widths or something. But here the centers are totally, well, some of the centers are very well separated. The 600 nanosecond Gaussian with the 50 nanosecond inverse filter function have a strong overlap. This happens to have a pretty slowly decaying tail. Gaussian has a very strong, fast decaying tail. So you see that these guys are being mixed up. The 600 nanosecond Gaussian. Here is the confusion matrix and the accuracy accuracy as a function of shots curve. And the linear classifier is basically random guessing one for. And yeah, as we saw here, the confusion is primarily between this inverse Gaussian or the inverse filter function log with Gaussian. Okay. So I will go through this a little fast. Well, so yeah, so we can one of the nice things about this output feature encoding, take a look at what measurements or what about the measurements, what information is relevant for performing the classification. So one thing we did was let's take a look at the covariance of the measurements that are interspersed throughout the evolution. And what we did is we truncate the amount of correlation that we're allowed to have at the time. Right. So here, let's construct our output feature by only looking at diagonal and let's say the first diagonal. So that would be DH one, DH of the so-called Hamming distance. And and what we did is we took a look at the we sort of broke up this task into two different tasks, looking at sort of the time scale of each one. So here we have like just the 50 nanosecond filter width. These are sort of very fast signals. And we try to just look at the classification accuracy of distinguishing between those. And then as well as the sort of long correlation time signals. And what we found was, as we play around with the output feature for the 50 nanosecond task, where the signals are changing much faster than the measurement rate, the sort of the first order moment was basically all you needed to capture the information of the classified. Whereas for the slowly varying signals, where the sort of information is changing at a rate of the measurements, the sort of correlations between the measurements is actually very, very important to do classification. So here is a function of the classification accuracy for the subtask, say 600 nanoseconds to 50 nanoseconds, where we just use we only used the truncated nth order central moment. And you see that, yeah, as like the 15 nanosecond, primarily the mean, whereas the 600 nanoseconds, as high as up to the third order central moment. Okay, cool. So I'll just spend a couple of slides looking at sort of future directions, outlook. So one thing we took a look at is like, how does it scale with larger system sizes? So there's a million ways to do this, but we generalized our system by just slapping on more qubits coupled to the resonator. You could have had, more resonators coupled to a single qubit. Whatever. We sort of just decided on this one, and we tried too much detail, but we basically took our same sort of unitary protocol and just generalized it for multiple, basically the same things. Basically tried to keep things as consistent as possible as the experiment, but just increase the number of qubits. And as yeah, and we basically get better performance as we increase the number of qubits. We require less shots as we increase the number of qubits, as sort of somewhat expected, hopefully expected. And so yeah, this is potentially interesting as a way to. I mean, one thing I haven't really commented on is that our system is nowhere close to any sort of quantum advantage, right? Computational advantage. We have a qubit coupled to an oscillator. It's a very, very small Hilbert space. My Apple Watch on low power mode could simulate that. But it's nice to see that as you scale up, the performance improves even more, and hopefully you can do more sophisticated tasks as well. And the nice thing with reservoir computing is, of course, the training will not suffer, at least not more than a classical system, as you increase it. The other thing that I sort of hinted at in the beginning of the talk is that the superconducting qubits provide a very natural interface with microwave signals. And this has been sort of been demonstrated in a few different experiments. But Benoit's group basically, showed this microwave quantum advantage. It was purely, nothing to do with sort of computations, but just showed that you can have a quantum microwave radar that outperforms any sort of classical radars. And some superconducting qubits are also known for state-of-the-art detectors, dark matter detectors. And so, I mean, this was sort of part of the motivation behind the whole work is, we're not IBM, we don't have 500 qubits, and we're not going to try and get a computational quantum advantage. However, um, because we have some analog systems, and if our inputs can be analog, we've demonstrated they can. Our inputs can be analog, and we can perform classification on analog signals. Can you start performing computation on signals that you just wouldn't be able to do by because it's so low powered, it's so noisy, just a few photons, correct? And so this is sort of the regime that we want. We're very excited about. I mean, we have not, there's few technical difficulties between the experiments we performed and actually demonstrating this, but this is the direction we're very, very excited about. Demonstrating is sort of this combined sensing slash computation method, where you're using your quantum system to perform computation on some input that would basically be a sensing machine for low power. Okay, so that's basically the end of my talk. I just want to pull up this slide. So Sridhar and Vlad, I work very, very closely on this. Of course, Peter was supervising along with Hero and Logan. Vala provided lots of technical expertise. And Jeremy was sort of an early contributor early on before he left for MIT. And a bunch of theory work was provided by thanks to Job. Cool. So yeah, just the last slide to summarize things. Yeah, the main contribution is that we were able to perform these computations on these analog microwave signals, super low amount of photons. And as I mentioned, I'm very excited about combining this work with circuit sensing to open up the possibility of achieving competition in the package. Yeah, thank you.
Thank you so much, Alan. This is a really, really interesting work and also a very clear and well done presentation. So thank you on both accounts for that. We do have time for questions, short time, but I'll go ahead and end the recording here, and we'll have time if folks want to stay after for questions. So thank you again to Alan for this really, really nice talk.
Thanks. Yeah.